Hey everybody, Mr. Covey here. Okay, thanks for coming back and watching this. We're going to go through one more example of this finding speeds, and we're really going to emphasize the difference between average speed and instantaneous speed. Okay, the difference between speed over an interval of time and your speed at 1 second, 1 millisecond, in a single instance. Okay? So, same type of situation here. You got this guy, Tour de France, riding his bike. Here's his distance. X is time in hours. D is distance kilometers. Okay, first question. The race was 100 kilometers. How long did it take him to finish? Oh, okay. They're just telling me a distance and asking me to find the time. They're just asking me to solve this equation. Again, you could solve this equation by doing quadratic formula. I just think it's easier to do on your calculator, and I want to make sure you remember how to do that, just as a general thing. So grab your calculator, go to y equals, put in 0.4x squared plus 18x as y1, y2 is 100, go to your window, and let's talk about this for a second. X is time in hours. You don't have negative time, so I'll start at 0. How long does it take you to run, or excuse me, to ride 100 kilometers? I don't know, whatever, we'll make it 10. Y is distance. We're not doing negative distance, so we're going to start at 0. We're trying to see how long it takes them to ride 100 kilometers. We're trying to figure out that intersection, but I'm going to make it 150 just so I can have like a little bit of, I can see a little bit above that horizontal line. Okay, so I'm trying to figure out where these graphs crisscross. I got them both graphed. Second calc, trying to figure out where they intersect. Enter, enter, enter at 5. Okay. So at x equals 5 hours is how long it took him to ride 100 kilometers. Okay. Second question, how far had he ridden? 2 hours and 20 minutes into the race. Okay, they're just telling me a time, asking me for distance. Nothing with speed here. Okay. So I'm going to do D, and I'm going to plug in, well, 2 hours and 20 minutes. That's 2 1/3 hours. 2.3333. 2 1/3. That is 8/3 hours. And I'm just plugging that into my function. So I'm just doing 0.4 times 8/3 squared plus 18 times 8/3. Figuring out how far he'd gone. After 2 hours and 20 minutes, he'd gone 50.844 kilometers. Okay. Just plug it in for an x value, plug it in for a y value. Stuff you guys know. Okay. Average speed for the entire race. Okay. I'm going to use my difference quotient here. Because I'm trying to find speed, I'm trying to find slope. Remember, difference quotient tells us slope. Slope of a distance versus time graph is speed. What's the x value I'm starting to measure the slope at? 0. How far apart is the second x value? I want to do it till the end of the race. So it's 5 hours later. How far is it from 0 to 5? 5. Now I'm going to do my difference quotient. D of x plus h minus d of x all over h. Okay, so it's d of 5 minus d of 0 divided by 5. What's d of 5? How far had he gone after 5 hours? Well, he'd done the whole race. He'd gone 100 kilometers. How far had he gone after 0? Well, he hadn't gone anywhere. Divided by 5, 20 kilometers per hour. Okay. Oops, sorry. Second one. Average speed for the first half of the race. Okay, well, first half, I'm still starting at time 0. That's my first x value. How far away do I want to use that second x value? Well, half of the race. So I only want to do it 2.5 hours later. I'm going to do my difference quotient. Okay, this is finding slope, and slope in distance versus time graph is speed. Toss that in my calculator. I got 19 kilometers per hour. Okay, so for the first half of the race, his average speed was 19 kilometers per hour. Okay, let's do the second half. Well, what's the first x value I'm going to use? Well, I'm only doing the second half, so the first x value is going to be 2.5 hours in. And then I'm going to take another measurement. I'm going to find the slope between x is 2.5 and x is 5, which is 2.5 hours later. Do my difference quotient. X plus h minus d of x all over h. And I got that the slope, the speed, was 21 kilometers per hour for the second half of the race. What does that tell you about the part D and part E? Tell you about his ride? Well, it tells you, sorry. that in the first half of the race he was riding slow, and the second half he sped up, so that overall he was riding 20. Okay, cool. Okay, now for the real tricky thing. I want to know, how fast was he riding exactly 2 hours into the race? Okay, so I'm going to say when's the, I'm trying to find the slope. I'm going to find the slope between an x value of 2, and then I want that second x value to be really, really close. Okay, like super close. Why? Because his speed could change a lot. Like if I had used 2 hours and 2.5 hours, well, I'd be getting his average speed between 2 and 2.5 hours. That wouldn't tell me how fast he was riding 2 hours into it, because he might have changed his speed a lot between 2 and 2.5 hours. Maybe like he hit a hill and he had to slow down or something. So I want to do like 2 hours and 2 hours and 1 minute. But what would be better than 2 hours and 2 hours and 1 minute? So I can do H is like 0.1, like 0.1 hours later. Or I can make H like even smaller. So I can make that second point like really close to that first point, like 0.01. Or I could make that H like even closer. I know what you're thinking. Just make it 0, Mr. Covey. All right, I'll make it 0. Okay, so let's see. If I make it 0, watch what happens. D of x plus H minus D of x all over H. That's D of 2 minus D of 2 over 0. This is getting messed up. What's D of 2 minus D of 2 is 0 over 0. What's 0? This is undefined. This is all messed up. So I can't just use H equals 0. But I want H to be really close to 0. I hope at this point you're screaming at your computer. You're like, Mr. Coffee, what have you been doing the last 3 weeks? What have we been doing in class? Why are we talking about this? We want an H value to get really close to 0, but not be exactly 0. That's called a limit. Oh. So you want to do the limit as that second point gets really close to 0. Or the distance between the points gets really close to 0, rather. You want that H, that distance between the points, to be really close to 0, so that you're measuring the average speed between 2 hours and 2.0000001 hours, which is basically just going to tell you the average speed, 2 hours. Okay. We will formalize this idea next week and how you actually use a limit. Okay, we'll save that for next week. But I want to show you a thing I put on Desmos, or a thing I put on Schoology that's a Desmos thing that you can mess around with this idea of finding slope between 2 points. When those points become closer and closer together, they merge into one. The distance between those points approaches 0. Okay, so here's a little thing I put on Schoology. And I'm just going to show you how it works. So what they're using is the letter A for the first x value. So let's say when our first x value, like in our example we did, was at 2. And they have a different graph plugged in here than we use, but the idea is the same. Okay. So we have our first x value at 2. And in this case, right now, we're doing the speed with the second x value being 1 away. But you see what happens here, and maybe if we zoom in a little bit, it'll look a little cooler. Actually, I'm going to move this point over just for argument's sake. I'm going to make it whatever, some x value there. So right now, we're clearly doing an average speed, an average slope between 2 points. I don't think I mentioned my name in the other video that this is called a secant line. When it cuts through, it's between 2 points, it's a secant line. So we're finding average speed, we're finding slope of a secant line. What happens is when the distance between those 2 points gets closer and closer together, or excuse me, they get smaller and smaller, those points get closer and closer and closer together until they like merge into one. And what happens is that secant line becomes less secant, it does less cutting, and then right here, it's no longer a secant line. It's a different type of line. It's a line that just touches the curve at one point. You might remember from geometry, a line that just touches a circle is called a tangent line, as opposed to a secant line, which cuts through a circle. Those same words here. So your tangent line becomes your secant line becomes a tangent. Anyway, we'll get into those ideas more when we look at the limit definition of the difference quotient of the derivative next week. Thanks for watching. Mess around with this if you want. It's cool.